We describe processes as being exothermic or endothermic. An exothermic process releases heat to the surroundings. So the system releases heat to the surroundings to be exothermic. So heat is flowing out the system into the surroundings. You would think that if heat is flowing out of the system into surroundings, then the system might be getting cold. It's losing heat. But the only way that heat can flow out of the system is if the system is hotter than surroundings. So it's losing heat, but it's losing heat to bring a hot system down to the temperature of the surroundings. So the system is hot, hotter than surroundings to be exothermic. An endothermic process absorbs heat from the surroundings. So for this to occur, the system has to get cold. The only way for heat to flow from the surroundings to the system is if the surroundings are hotter than the system. So the system has to get cold so heat can flow from the surroundings to the system. The system gets cold by converting heat energy inside the system into a chemical potential energy inside the system. This process of converting heat into chemical potential reduces the temperature of the system, allowing heat to flow in from the surroundings. So if we have energy flow in and out of the system through either the process of heat or work, how do we measure the energy of the system? We call that measure of energy the internal energy. So the internal energy of a system is the sum of all kinetic and potential energies of all the particles in the system. This is hard to define. So it's easier to define the change of internal energy, the flow of internal energy in and out of the system. So this internal energy is going to include all the motion of all the molecules in the system, all the heat motion of the molecules. It will also contain all the potential energy of the chemical combinations in the system. But with potential energies, different reactions can extract different amounts of those potential energies. This leaves the potential energies hard to define. But we can measure the change of energy. Change of energy. We always measure change, delta energy, in terms of final minus initial. Final minus initial. But in this case, the flow of the energy is going to be through two processes, heat and work. So we're going to use Q to represent heat and W to represent work. So our change of internal energy is going to be the sum of Q plus work. Q plus work are transfer processes. These are the energies being transferred between the system and the surrounding. So these systems will both contain a value, a magnitude in joules, and a sign that represents the direction of flow. If the flow is out, then we're going to have a negative value. If we lose energy, we're going to have a negative value. So if we have a higher initial energy, internal energy, and a lower final, that means we've lost energy. Then final minus initial, small minus large, will give us a negative delta E. So if we lose heat, we'll have a negative heat. If we do work, we have a negative work. If energy is transferred into the system, it will be positive. So if energy is transferred into the system, we're going to have a higher, larger final energy. large minus small will give us a positive delta E. So positive heat is heat flowing into the system. Positive work is work being done onto the system. In these types of problems, the language usually gives us the sign of heat and work. So in our example down here, gas absorbs 98 kilojoules. Absorbs is the endothermic process. Receives would be endothermic process. Releases would be exothermic. Gives off exothermic. So if it absorbs the endothermic process, that means our 98 kilojoules is going to be positive. For work, if it does work, this is giving the energy away. So that's similar to exothermic. So if it does work, it's giving energy away, and that's going to be a negative energy. If work is done on it, that would be endothermic and it would be positive. So in these problems, the language gives us a sign of the heat and the work. By paying attention to the language, we'll figure out the sign. And then the delta E, the change in internal energy, is the sum of heat plus work. So in this case, it receives the heat, positive value. It does the work, negative value. So heat minus work, 98 minus 15 kilojoules, means that we have an increase of 83 kilojoules. So this process would be endothermic for this system. It receives energy. We have two types of properties: state and path. A state function or a state property depends only upon the initial and final states of the function. For the change, we usually are looking at the changes. So it only depends upon for the change in a state function, we are only dependent upon the initial and final states. We do not care what happens in between the initial and final states. We just need to know the initial and final states, and we'll know the change in that property. So for state functions, energy is a state function. Internal energy is a state function. It only depends upon the initial and final states. Enthalpy, which is heat at constant pressure, is also a state function. The funny thing is how internal energy is sum of heat and work. Internal energy is a state function, but heat and work are not state functions. Heat and work are called path functions. Path functions we cannot calculate from the initial and final properties. Path functions depend upon the complete path between the initial and final state. So path functions. If we want to drive from here to San Francisco, we could drive up the 5 freeway. It takes a certain amount of miles to get there. If we go up the 99 freeway and go through Sacramento to get to San Francisco, it takes more miles. So the miles of driving are path functions. It depends on the particular route taking between the initial and final states. There are multiple types of work available. Work is doing push against a force. We are going to primarily look at what is called PV work, pressure volume work. So this is the process of internal combustion engine, steam engine. We blow up a gas inside a cylinder. It creates a lot of pressure, and it expands the cylinder by pushing against a piston. This is pressure volume work. It's the pressure pushing on a wall to change the volume. Pressure volume work. We're going to look at a simple version of this. The complete version of this would be include partial derivatives and integrals. But if we can hold pressure constant, and this is the pressure that is being pushed against. So in the piston pressure, if it's going to push, it has to be higher than the external pressure, higher than the pressure on the piston. But if the pressure on the piston is constant, the math of calculating work becomes simple. In terms of math, the work becomes pressure times change in volume. So if the external pressure is constant, that's the smaller of the two pressures, then work is pressure times the change in volume. In this equation we have a negative sign. Why do we have a negative sign? Well, if we're pushing against external pressure, the external pressure is going to be positive. If we're blowing up a gas mixture in a cylinder, the cylinder is going to expand. Delta V is going to be positive. But this system, this expanding gas system, is pushing on external pressure on the piston. This system is transferring force, energy, to this piston. So this system, this exploding gas system, is giving up energy to the piston. It's doing work. It's losing energy. It's an exothermic style process, which means that work has to be negative. That's what this negative represents. It represents that a positive delta V, a increase in volume, corresponds to a doing work, a loss of energy. If we were compressing a gas in a volume, then we would have a negative delta V, but it would be receiving energy. This negative would make it positive to show that it would be receiving energy in endothermic process. If we use our units in terms of liters for volume and atmospheres for pressure, liter atmosphere is an acceptable work unit. But we usually like to get over to the SI unit of joules. So a conversion unit we need to learn is 1 liter atmosphere is 101.3 joules.